This is a sunrise on Earth, as no one will ever see it, but it is our sun nevertheless. Only with X-ray vision could we see this, but not from the surface of the Earth. This remarkable image was obtained by the Yoco X-ray telescope, orbiting high above our atmosphere. Another satellite, Solar Max, recorded this image in ultraviolet light. And this radio image of our sun was made by the Very Large Array in New Mexico. Only when an eclipse blocks the full glare of the sun can we glimpse with our own eyes some of the magnificent features of our normally invisible sun. Highly magnified, the surface of the visible sun, the photosphere, looks like this: porridge-like granules of upwelling plasma at a temperature of almost 6,000 Kelvin. And that's all we would see if the sun had no magnetic field. In fact, we see a lot more different features, such as sunspots and huge arching prominences reaching hundreds of thousands of kilometers into space, and tremendous explosions of energy and flares. All dramatic evidence of unseen magnetic forces. To investigate these phenomena, astronomers must look right across the spectrum, from radio waves, through visible and ultraviolet, to X-rays and gamma rays.
Even though our sun is 93 million miles away, that's as close as we'll ever get to a star. And even with the most powerful telescopes, we can't see any features on the other stars. Yet with our solar telescopes, we can zoom in and see all kinds of interesting and wonderful phenomena on the surface of our sun. So let's go have a look at our own star today and see what it's doing.
Only an earthquake in June 1992 managed to stop Zirin and his colleagues for a few months from their continuous sun watch. The observatory is sited on Big Bear Lake, high in the hills east of Los Angeles, to take full advantage of the clean mountain air and the stable atmosphere above the cool water. Under these near-perfect conditions, they can obtain superb images at visible wavelengths.
Al, this region has really developed rapidly since this morning. Notice that there's penumbra now around the entire leading umbra.
That's kind of the beginning of the end of its growth, but maybe these spots here will do it. It's funny, it just started out as this little thing yesterday. Anyway, here in the Big Bear Dome, we have a nest of 3 telescopes, which enables us to look at the sun in different scales because we're limited by the size of our film frame or our video frame. So we have one telescope that looks at the whole sun, one that looks at about a 25th of it, and one that really zooms in and gives us a high resolution. Now, the high resolution telescope, you need a big telescope, and you need to use a vacuum so you don't have a lot of air moving around inside the tank. And we throw away most of the light, maybe 9,999 parts out of 10,000 of the light we get. Then we also have to track very carefully because we're looking at things that are the size of a hotel in San Francisco as seen from here in Big Bear. So we have a very accurate tracking mechanism which follows the sun photoelectrically. Now the mirrors that are banging and clanking back and forth direct the light to different cameras and different filters of different wavelengths. If we looked in just normal light, we would only see the surface of the sun. When we use the very narrow filters, we can see the atmospheric phenomena, things moving around. Then finally, we can use these narrow filters to study the magnetic field, which really dominates what happens once you get above the surface of the sun. What happens is when the magnetic field is strong, the light is broken into rotating rightward and beams rotating leftward. And with our hardware, we can separate out these beams, put them in the computer, and subtract them, and determine what the direction and magnitude of the magnetic field is. Then we try to go back and understand how these strong magnetic fields generate big eruptions and solar flares.
Over the years, the running of this small observatory has generated one of the biggest libraries of solar events in the world.
Here in the lodge, we've accumulated a number of pictures of the sun, which show some of the things we're interested in. If you look at the surface without a filter, just in general white light, all you see is what we call granulation, a lot of convective clouds coming up to the surface. And the only aspect of the magnetism you detect is the sunspots, because in the sunspots, the field is so strong, it can dominate the pressure of all the gas there. But as you go higher into the atmosphere, the gas pressure reduces and the magnetic field remains strong till very soon it dominates. So when you look in our filter in hydrogen alpha, then the atmosphere is absorbent, and therefore we can see all the gases in the atmosphere. Now they have a wonderful loop shape because their motions are determined by the lines of force going from one magnetic field to the other. And that's what we see around the sunspot with a strong magnetic field. Because the sun is so large and the sunspot is relatively small, it's not accidental that the sunspot just comes up there. It's probably part of this whole three-dimensional structure of magnetic field that's coming up from inside the sun. Something seems to happen as it reaches the surface, which produces these twistings and stresses and the effects that produce solar eruptions. We see this over and over in this image here, where we see a burst of material squirting out from near the sunspot. What's actually happened is a new spot has come up next to the sunspot, and in making its peace with the existing magnetic fields, a lot of energy is released. And when the energy is released, you see it's trapped in the magnetic fields and therefore focused into this long ejection, which we call a surge. And here we see a bipolar sunspot. We see one sunspot of one magnetic field, and then the follower is of the opposite magnetic field. And there are lots of lines of force connecting them. In any given sunspot cycle, only one magnetic polarity will lead in each hemisphere. Now, around the back of this thing, we see a dark filament curling, and that's a cloud of gas which is up above the surface and scatters the light coming up from the surface. It sits on an area where the magnetic field is just changing between pointed towards us and pointed away from us. And in that area, the field lines will be horizontal, and that's why they keep the material up. When we look sidewise at the edge of the sun, we get some of the most graceful phenomena of curtains of this gas, somewhat like an aurora on the Earth, but different in the sense that this cloud may last for weeks. Now, they are supported by the magnetic field, but the odd thing is, when they finally give up the ghost, they don't fall down, they erupt outwards. And they'll erupt outwards in enormous clouds, which form what we call coronal mass ejections, and which may come out all the way to the Earth. Now, as the sunspots break up, the magnetic fields that are involved with them don't disappear, but they spread out over the surface. And if you look at almost any part of the sun with a sensitive enough magnetograph and take a long enough exposure, this particular one was 6,000 frames, you can see that there are magnetic fields almost everywhere. And they are moving around, and they are forming and reforming. And there's a peculiar effect in which they gradually drift up to the poles of the sun, and they reverse the polarity of the sun every 11 years. All the things we've looked at so far have been creatures of the magnetic field of the sun. And the big eruptions that we see are basically the result of rapid evolution and change in the magnetic field, which builds up a very strong stress, just like happens in earthquakes, where the crustal motions of the Earth store up energy, which is finally released. And in this movie, which we made of the magnetic evolution of one of the most active sunspot groups of all time, you can see how the motions of the magnetic field are changing the thing all the time. And if we were looking at it in hydrogen alpha, we would see the great eruptions that were produced by this rapid change in the magnetic field, which took place over a 6 or 7 day period. We feel that by studying these in detail, we can learn to understand and even predict the occurrence of this kind of activity.
If we could see the entire sun with magnetically sensitive eyes, it would look like a constantly changing bundle of twisted fields, curling between sunspots, stretching and reconnecting as magnetic energy is released in flare explosions. To see what happens to all this energy, we need to tune into the radio emissions produced by the accelerated electrons spiraling rapidly high up the magnetic loops. The most sensitive radio telescope on Earth at centimeter wavelengths is the VLA, the Very Large Array near Socorro in New Mexico. It has 27 dishes, each 25 meters in diameter, arranged along 3 arms up to 21 kilometers long. When all the dishes are close together, it is ideally suited to imaging rapid events over the entire sun. As the dishes are moved wider apart, they effectively zoom in to see smaller regions in finer detail.
The VLA has taught us a lot about the solar flare process, which you could not have done otherwise. For example, by observing at different wavelengths, you can actually observe several different layers of the sun's atmosphere and their effects in the sun's corona. So the difference in altitudes between them may be of the order of several tens of thousands of kilometers. The picture at 20 centimeter wavelength lies way above the picture that you saw at 6 centimeter wavelength, and this is primarily because the radio emission is generated by energetic electrons which spiral around the lines of force in the sun's corona. In other words, it actually maps the strength of the magnetic field in the flaring region. The magnetogram is at the photospheric level, whereas the computed field lines are in the corona, and the blob that you see actually is at an altitude of 130,000 kilometers, and the separation between the 2 foot points is something like 200,000 kilometers. And this particular burst lasted only about 3 seconds because the beaming electrons actually took that much time to move from one foot point to the other foot point. You also notice that the same thing is happening over and over again. It is due to a succession of radio-emitting electrons propagating from one foot point to another foot point at very high speeds of the order of 1/3 the velocity of light. And that explains why these bursts are so rapid and last only a short time.
Such flares also emit X-rays and gamma rays, which, unlike radio waves, do not penetrate the Earth's atmosphere. This hard X-ray imaging telescope, called HIDI, will be carried by a high-altitude balloon over 40 kilometers high to record solar flares. It is designed to stay up there for 8 hours or more. Why does it have to be so long?
The reason is that hard X-rays and gamma rays can't be focused by lenses or mirrors. We need to use another trick, and the trick we use is analogous to that of a pinhole camera. We use grids. This is a sample about 1 centimeter thick, made out of tungsten, a very dense material. The grids, about this diameter, have slits and slats in them. The slits let hard X-rays and gamma rays pass. The slats are thick enough to actually stop the energetic radiation that we're trying to image. Now, what we have done in the actual balloon payload is use pairs of these. The pair works together something like this. What I have here is a film that's actually a contact print of the grid that I just showed you. If I have them so that the slits on one piece of film cover the slats in another, you can't see through it. But if I move them, keep them straight, you see the opening, and now the light, analogous to the hard X-rays and gamma rays, can pass. Move it again, and I can close them up again. So that's how it really works. Except that we separate it by large distances, to get very fine angular resolution out of the system. When the telescope is actually operating, the grids rotate synchronously to give us the opportunity to reconstruct images of the sun and its solar flares in 2 dimensions.
To understand the complete picture of the sun's atmosphere, we've had to open up regions of the electromagnetic spectrum that are accessible only from rockets and satellites, namely the X-rays and ultraviolet regions. For example, this ultraviolet image here shows the network structure that is much coarser than granulation, like a hairnet stretching across the sun. In close-up, we can see the hairnet structure in more detail, and a thin, very hot transition layer at temperatures of 100,000 degrees, just above the much cooler photosphere. We can also see a faint loop stretching high into the even hotter corona. The temperatures in the corona can be as high as 2 million degrees. Computer modeling has shown that plasma waves driven by magnetic forces can provide much of the heating. When particles are moving this rapidly, they emit X-rays by collisions with one another. This picture of the sun was taken with a rocket-borne X-ray camera. It shows plenty of flare activity, especially above sunspots. The temperatures here can reach 20 million degrees or higher, enough to trigger short bursts of nuclear fusion. And in 1991, the Japanese Yoko satellite provided this spectacular series of images, revealing a wealth of detail never seen before.
We see phenomena on both local and global scales, from tiny transient brightenings in dark coronal holes to vast interacting loops and flares. At the edge of the sun, these loops may be seen as great arches of matter, lifting free of the sun's gravitational pull, driven by flare energy. Sometimes a cloud of this matter escapes and starts a long journey across the solar system, a coronal mass ejection event. The clouds grow too dim for direct imaging, but they can still be followed.
We can track these clouds by looking at the scintillation or twinkling of radio sources around the entire sky. Just as a star twinkles when you look at it through the Earth's atmosphere, a radio star twinkles when you look at it through these coronal mass ejected clouds. In this full sky scintillation map, the sun is just north of center, and the red regions are regions where the radio stars are scintillating very significantly. So this enormous red region to the upper left shows a large mass ejection cloud passing just to the left of the Earth as you look towards the sun. To the right of the image, we see a quiet sky where we simply see the mottled effect because of the radio sources themselves. There is no event in the solar system in that location. Clearly, some of these clouds can collide with the Earth and have dramatic effects. Not all of these effects are as beautiful as the aurora, where electrons enter the upper atmosphere and can interact with the oxygen and nitrogen atoms, causing beautiful displays of light. The magnetic fields of the mass-ejected clouds and the Earth itself can interact, and that can cause significant navigational problems. It can cause significant pulses in power-generating circuits and a whole host of other effects. Fortunately, most of the mass-ejected clouds will miss the Earth and just travel out through the solar system. But how far do they go? What do they do beyond the Earth's orbit? Well, the Voyager spacecraft have now passed beyond Pluto and Neptune, the 2 outermost planets, as they pass through the solar system. Recently, they have detected radio emission apparently coming into the solar system of frequency about 1 kilohertz. This radio emission seems to coincide with the time that coronal mass ejections reach the outer reaches of the solar system, and it seems that the mass-ejected events in fact are interacting with the very edge of the solar system, the heliopause, which is where the magnetic fields of the solar system literally merge into the magnetic fields of interstellar space. So after their phenomenally successful planetary mission, it seems that the Voyager spacecraft are now giving us information on the very edge of the solar system.
As we've seen, astronomers can now combine optical and radio images from Earth with images from space to open up the entire spectrum, including the infrared, ultraviolet, as well as X-rays and gamma rays. Each wavelength region probes different levels of the sun's atmosphere. Only by looking through all these windows can we begin to see how it all works. Will all this data be enough? Is our sun special, or can we see similar phenomena on other stars? Here in California, at the Center of Extreme Ultraviolet Astrophysics, they have detected huge flares on other stars.
All stars, except for our sun, look just like points of light, even with the world's largest telescopes. So the only way you can see a stellar flare is by looking for a sudden enhancement or brightening. When we were checking out the instrumentation on the Extreme Ultraviolet Explorer satellite, we were fortunate in detecting just such an enhancement. The intensity of the star increased almost a factor of 10 in a very short time. We were also fortunate in that we were using the spectrometers at that very same time. So we had a record of the spectrum of the flare while it was taking place, which we can compare with the spectrum obtained before the flare took place. And the results then tell us what are the plasma conditions in this stellar flare. The flare we saw was some hundreds of times more intense than any flare ever seen on the sun, which is rather a good thing, actually, since such an energetic event on the surface of the sun would have devastating effect to life on Earth. The upper atmosphere would be ionized and all communication would be disrupted. We'd have a daytime aurora, which would be quite spectacular, but in the long run, the ultraviolet light would reach the surface of the Earth with devastating consequences to life. The question is, why do these flares take place? Another question is, why is the corona, the outer reaches of the sun, have such a high temperature? It's at a temperature of several million degrees, but the surface of the star is only 6,000 degrees. How can such a cool surface heat up a high temperature corona? We don't know the answers to this, but we hope to find out by studying EUV radiation from other stars and see how they compare with our own sun.
So by investigating other nearby stars, we will be better able to understand our own star. New detectors and the ability to get above the atmosphere have given astronomers new eyes to look at the whole universe. And every window opened, even for our nearby sun, reveals new things about the universe and increases our understanding of our place in it.